So let's change gears and go to slightly lower level TensorFlow. Okay, we'll build 3 models, one for linear regression, then logistic regression, and then deep neural network. Okay, so this is how the model will look like now. We'll be using bunch of functions from Layer API, right? There are we talked about componentized view of machine learning. Do you remember? Componentized view. What are the 5 components? Training data, model, cost function, evaluation criteria, and optimization model. All right. So you can see here most of these convolution neural network functions: conv2D, maxpool 2D, flatten, fully connected, dropout. Right. We will talk about these functions in the lab. Right. There is a custom estimator lab where we will be looking after these functions. The point that I'm trying to drive is we are going to use functions from Layer API. So this will define convolution, pooling, and fully connected layers. Right. So this is the model, image model, right? Then we talk about loss metrics, right? So we have functions like softmax cross entropy. You know, there are a bunch of loss matrices defined, something like softmax cross entropy loss, right? Then we have sum of squared loss, sigmoid cross entropy loss, right? These are all loss functions that are defined by Layers API, right? Then we also talked about matrices, right? Various matrices that we use to evaluate machine learning algorithm, right? So we talked about accuracy, right? AUC, do you know AUC? Area under the curve. Okay, so let's say we have machine learning. Let's say we have a classification problem with 2 classes, right? Let's say +1 and -1, +1, -1, right? And let's say this side is actual labels, right? And this side is predicted. Okay? Now, if actual label is +1 and predicted is +1, right? What is it called? True positives. Right? So essentially confusion matrix is we fill up this particular table. We count how many times actual was +1 and predicted was also +1. Right? So we'll fill up entries for each one of them. Ideal confusion matrix should have 0 entries here. Right? That's where we have perfect classifier. Right? So you should only have entries for true positive and true negatives. Right? But life is hardly ideal. Right? So we also have some issues. So now the actual is +1 and predictor is -1. So this is a false negative. So this is false negative. Actual is -1, predicted is +1. This is called false positive. Correct? So this is the most important matrix that we get after we learn after we apply our model on the test data. Right? All of you agree, right? We report matrices on test data, not on the training data, right? If you find your training error to be 0, do you throw a party? That's a bad thing, right? We need to get good test error, right? Why are we doing machine learning? We want to generalize, right? Generalization is the key objective. So we should, the way we test generalization is by using some test data and reporting and evaluating performance on the test data. Only if we find it comparable on the test data, then only we say that we have a model. Okay? And from this matrix, there are a bunch of statistics that are derived. One is precision. Right? What is precision? How precise am I with my, let's say, label of +1? Right? So predicted are true positive, and how many of them are predicted as plus 1, Tp plus Fp, right? So Tp by Tp plus Fp is my precision. Okay? This is the percentage of plus 1 that are correct. Correct, and second metric is recall. Recall is Tp by Tp plus Fn. So what percentage of plus 1 I was able to predict correctly, right? So I have, these are my correctly predicted, and actual plus 1 Tp plus Fn. Got it? And what is the accuracy? What is the accuracy? Tp plus Tn divided by everything, right? Tp plus Fp plus Fn plus Tn. Then we also draw couple of other graphs, right? One of the graph is called ROC curve, which is receiver operating characteristics curve, right? Which tells us how our classifier performs across various thresholds, right? Imagine you have a logistic regression classifier. Everybody knows what is logistic regression, right? We take linear combination, right, theta transpose x, and we pass it through sigmoid function, right? And we get either, we essentially get plus 1 or minus 1 output. At the same time, we can also get probability, right? The real number is squashed between 0 to 1, and there is a probabilistic interpretation to that. So if I take the probability of each example and say that I'm going to divide, so now we have number between 0 to 1, right? This is my line between 0 to 1, right? And I have to draw a threshold somewhere, right? Below that I'll say that these are negative examples, these are positive examples, right? So I can try different kind of thresholds, and for every threshold I'll calculate what is called as, I think this is false positive rate and true positive rate, right? I take a threshold, and for that threshold I calculate FPR, TPR, right? I get a point, right? And then I keep repeating this process. So I get another point, third point, fourth point. So I'll get curve like this, for example, right? Ideal curve should be like this. Ideal curve should be like this, right? And if you have a random classifier, you have exactly diagonal kind of thing. So if your TPR, FPR, TPR curve is below this, then you have really bad classifier. If your TPR, FPR like this is no good. Clear? ROC? And then we calculate what is called as area under the curve. So imagine this is your graph. So we find out what is the maximum area under the curve. That is called AUC measure for us. Area under the curve, right? And ideal one is AUC of 1. AUC of 1 is the best, right? And for this guy, I get AUC of 0.5. Anything below 0.5 is bad. So it will be between 0.5 to 1. Closer to 1 is ideal. Okay? So that's AUC for you. Yeah, so all these kind of measures are already written in TensorFlow. You don't have to write them by hand. Okay, so now we have 3 labs. Let's say let's take 1 hour to do 3 labs, 20 minutes each. Okay, so let me walk you through the linear regression lab. So this is the first lab, linear regression low level. Okay, I'll first walk you through the lab and then you can look at it, okay, on your own. Okay, so now our sessions and default graphs are back, right? We talked about sessions and graphs, right, in the beginning. Then we never used it because we were using canned estimator. Now we'll use the basic TensorFlow, right, along with Layers API and build machine learning algorithms. Okay. So the first one is linear regression. Okay. So what we have done is we have written a function to generate noisy data, right, with parameters m as 0.1 and b as 0.3. We are using mx plus b, which is standard equation of line, and we are adding some Gaussian noise to it, some small noise, right, and that's how we are getting our data. So, okay, so the first step in machine learning algorithm is to get train data and test data. So we use make noisy data, I get training and test, training data, training features and training labels. I call the same function and get test features and test labels, correct? I'll run this for you and let's see what's happening. Right, let's plot our training data. So this is how our data is generated, right? Now what we'll do is we'll use linear regression and retrieve the same parameters that we used to generate the data. Let's see whether we are successful about it, okay? Now as I said earlier, right, we talked about placeholders, right? So for the inputs I'll use placeholder. So you may be wondering what is this name scope input, right? So this is used for scoping the variables. So let's say if you have a huge data flow graph, you do not really know the scope of the variables, and so name scope helps you to scope the variables. And this is also useful because you get a much compact output in the tensor board if you do scoping properly, right? So within input scope, I am defining x placeholder, x underscore placeholder, and y underscore placeholder. Right? I am not defining any shape, I am saying that they are of the type float and their name is x input and y input. Right? So let's execute this. Right? I am not, now let's define the model. Now look at this, now we have another construct called variable, right? M and B are variable because every iteration of gradient descent I am going to change my M and B. So M and B are variables, right? And I am defining my model as y is equal to m into x placeholder, x underscore placeholder plus b. That's my model. So far so good? Yes. Which one? Placeholder? Yeah. So placeholder is some kind of a promise. I tell TensorFlow that look, I'm defining a placeholder where I give you a promise that I'll input some data later. So whatever input data you want to put inside machine learning algorithm, so especially features and labels, we normally use placeholders for that. And then we have variables, right? These are the variables which take different values in the course of model training. We use them as variables. So M and B are more like variables for us. Name scope, right? So name scope is, this is just like a scoping. So I'm saying that I'm defining these two variables, x underscore placeholder and y underscore placeholder, under scope input. Under the scope input, I'm actually using the scope under this input, right? I have highlighted it there, right? So I do this because, okay, if what happens if I don't use the scopes? If you look at the TensorFlow graph in TensorBoard without scope, you will see a lot of nodes without really knowing what part, where does certain nodes belong to. By putting this name underscore scope, I'm saying that x underscore placeholder and y underscore placeholder, these two nodes are dealing with input. Right? So this is more for organizational perspective. And yeah, not really classifying, but I'm saying that I'm using x placeholder and y placeholder under the scope input here. Okay. So if you look at the TensorBoard later, after executing this, you will see that their names are also slash input slash x placeholder. So they get some kind of a hierarchical name because of this. And it becomes better because if you are writing, let's say, a very large model, there is a possibility that you will use the same variable name somewhere else. And then there is a possibility of getting your data corrupted, right? So that's why the scoping is really, really useful. So scoping is a good practice that you should follow whenever you're writing TensorFlow program.
So apart from the appearance of the TensorBoard, does it make any other logical difference when you execute the code without a scope?
It doesn't make any difference. but you will have to be super careful in naming your variable, right? Any other questions? All right. So we execute this. Okay. So notice this, right? I have not yet, I have defined a session, but I have not done session.run, right? So when I printed m, b and y, you see them as variables. And look at the names. Now this is model, right? I use model here. So model underscore 1, n0, m0, model underscore 1, b0, and add 0. So you see the name now. Now earlier it used to be add colon 0. Now model underscore 1 is added here. Right? That's because of scope. And I know shapes for this. I'm not sure the shape for this. That's why there is a question mark. And they are of the type float. Right? Next, I'm going to define my loss function. Right? We have defined our model. Let's define our loss function. So learning rate of 0.5. We are defining a loss. My loss is basically a squared loss. Right? So there I do square of y, the actual value, and the predicted value, and this is the actual value, y placeholder. Because this is a predicted value, y is equal to m x underscore placeholder plus p. Y underscore placeholder is the actual value, this is a predicted value. I want to reduce the mean of the square error, right? That's my loss. Then under scope optimizer, I select gradient descent optimizer, right? tf.train.gradient descent optimizer. I specify learning rate for that, and I get a train operator, which is I say that optimizer.minimize loss. I get a train operator here, right? Let's execute this and let's run this. Now you can see that this is training optimizer gradient descent update model, right? So you now see the names in a hierarchical fashion, right? So there is a scope training. Within training, there is another scope loss. Within that, there is mean 0. So you can see with scoping, we are getting much better naming convention. Okay. Let's set up a tensor board. Okay. Somebody was asking me this in the morning. How do you initialize variables? Right. So this is how you initialize the variables. Right. This is most important thing. This is one of the very, very important things. Never forget to initialize the variables. Otherwise, you will get errors. Right. So we do session.run tf.global underscore variable underscore initializers. Right. This helps you to initialize all your variables. Now that we have initialized the variable, we are going to do the training.
Is there any other type of initializer other than that particular?
No, this is how you initialize a variable. Sometimes what happens is that you can also initialize variable where you are defining variables. At times variables also you can define initialize the variables. That is also possible. But this is irrespective of that, you should call this anyways. Then all the variables get initialized. Either to the default initial value or whatever initial value that you have specified at the time of variable initialization. Then I am specifying that I want to take 201 steps, right? And I do session.run with summary op and train, right? Summary op is something, okay, I have not executed this. So I am saying that I want summary, right? In summary, I want histogram of m, b, and I want the final figure of the loss. So I define these TF summaries, and these TF summaries will be added to your tensor board. So run this, and let's run this. Now this is where we are doing training of our model, right? So you can see how much more code you have to write if you use tf.layer API. That's one way of looking at it. But the other way is realize the power, right? Now you have all the power in your hand to decide whichever cost function you want to use or whatever optimizer you want to use. You can choose that for your own purpose, right? So I do session.run, then add summary, and then every 20 step I'm going to record m and b value. Okay. So let's run this. Clearing the output. I'm running. So now you can see that every 20 steps I'm printing m value and b value. And this is a step. So at 0th step we started with m of minus 0.47, b of 0.94. And ultimately you reach to value of m as 0.0 0.097 and value of, yeah, so this is m and b is 0.30. You will recall that we started with the same thing, right? Our m was 0.1 and b was 0.3, right? And you can, and we managed to recover that, right? This is very close to 0.1, right? And this is 0.3, right? I'll again print it for us so you can see that. Okay. And now if you want to make prediction, you can put, you can use feed dictionary and give X placeholder. Let's say for 2, let's see what is the prediction for 2. It's 0.497, right? 0.2 into 0.1 plus 0.3. Okay, so this was the first lab. Do you want to go through this lab? Huh? Take 15 minutes and go through the lab. It won't take much time, right? And then we will do in the same manner logistic regression and DNN. Right? Instead of doing all the 3 labs together, I did this. Now you go through it. Take 10 minutes, right? We'll start at 3. Okay. Let's start the second one. Okay. Now here we will use again the MNIST data set. That is our favorite, and we will be now building our own logistic regression classifier. Right. The thing to notice is now we will be having a different data set, but you will see that we will do pretty much the same things as far as loss function and optimizer definition goes. Okay. So that's the magic of TensorFlow. It figures out automatically how to compute the gradient. Okay. So let's start. I define a session. I have a default graph. I'm going to reset my default graph here. I'm reading the data set. Right. Fortunately, I don't have to go to the internet. I define number of classes 10, number of pixels 28 by 28, training steps 2000, batch size of 100, and learning rate of 0.5. Okay. That I defined here. I hope all you understand these concepts, right? Then we define placeholders, right? One placeholder we call it as images. The shape is none, number of pixels. I have specified none here because I do not know in advance how many examples are coming, right? And in the same manner, labels, none, and number of classes. Okay, I'll define my model. I have W and B, and I do matrix multiplication of examples with W, and I add B to it. That is my Y, right? This is my model. And then I define what is called as cross entropy loss, softmax. I use softmax because I have multiple classes, more than 2 classes. That's why I use softmax. And I'm using gradient descent optimizer. Okay. Logit is basically logistic regression kind of logistic function. Logit is logistic function. Okay. So I define loss. Okay. I think I have not done this. Okay. I run. I initialize all the variables, and I start training. Accuracy is around 90%. This is what we also got, right? When we were doing logistic regression with canned estimators, correct? So you can see that easily you can write production grade machine learning models, even using low level APIs. Right? That's because we have all layers written here, right? Let's try to see the input image was 7, and we also predicted 7 here. Okay. So this is the second code lab. I will again run the third one, and then you take both of them and take 20 minutes and finish it off. Okay, so the third one is for neural networks. Right, here we will use, instead of gradient descent, we'll use Adam optimizer. Okay. Okay. I did the same thing. I read all the data again, MNIST classifier. Okay. Now this is where it is important. So I'm going to use 2 hidden layers, each hidden layer with 500 units. Okay, number of classes is 10, pixel is 28 by 28. I want to train for 2000 steps with batch size of 100 and learning rate of 0.001. Okay, so this part was easy. We have already looked at placeholders, so okay, now this is where we will spend some time. Now I will define a function, right, that will help me create a layer in the neural network. Okay, so fc underscore layer is a function, fully connected layer, right. Okay, it takes arguments as input, size of the output, name is fc, and activation is done. Does everyone understand neural networks? One way to view a neural network is stack of logistic regressions, right? It will be clear in a minute why I am saying so. So let's say I have inputs like x1, x2, and x3. These are my features. Okay, let's say these are input to my neural network model. I'll have a basic neural network here, basic neural network. So what happens, right? So I have weights on each of the connection, right? Plus I also have a bias that I add, right? And the basic computation that we do is I take W1 x1 plus W2 x2 plus W3 x3 plus B, right? Essential linear combination. That's what I do here. Let's call it as Z. So this is what is Z, right? And then I take this Z and apply some kind of an activation function on it. G is the activation function on it, right? So this activation function, there are multiple activation functions that you can use. One of the activation function is logistic regression or a sigmoid function, right? So this goes between 0 to 1 and crosses at 0.5, right? And this is the entire real line, correct? This is your Z and this is your G of Z. So you do the linear combination, whatever is the output of this, you pass it to sigmoid, right? And depending on what values you have, you get the output over here. If you have large value of Z, you are likely to get output of 1. If you have large negative value here, you are likely to get output of 0. Clear? This is one of the activation function. This is sigmoid. Another one is, which is mostly used, is this ReLU activation function, rectified linear units. So this is your Z. So ReLU is 0 for all the negative values, okay? And then it linearly goes up like this. This is another activation unit, okay? There are a bunch of such other activation units like TANH, softmax, whatever, okay? Got the basic unit. Now what we do is, we take such basic units, right? In the hidden layer, you have multiple such kind of units, and each of your input is connected to that. That's why I say it's a stack of logistic regression model. And because we are using such kind of nonlinear activations, we are able to fit complex functions using neural network. Are you getting my point? Right? Otherwise, imagine if this G is a linear function, right? We wouldn't be able to learn any nonlinear functions here, right? Because I have linear function, I'm applying some linear activation on that, it still remains linear. Got it? So the nonlinearity neural network is coming from the activation, nonlinear activation, right? And the final layer in neural network, we normally use sigmoid as an activation function there. If you have 2 classes, we use sigmoid. If you have multiple classes, we normally use softmax. Got it? In case of classification. In case of regression, whatever output you get, you just pass it. Okay, so this was important to know why we are writing this function like this. Now it will be clear. There is some input size, right? I'm defining weight W and B, right? And I'm defining Wx plus B. This is that Wx plus B, right? That is Z, which is matrix multiplication between input and the weight, and I'm adding the bias term to it. Okay? And if there is an activation, I return activation Wx plus B. Otherwise, I just return Wx plus B. Okay? Now that we have defined this layer function, let's see how to define. Now defining neural network will be super easy. Okay, so let's define this neural network layer. So I defined my first layer, which takes images, which is my input. I want 500 or number of units here. I call it as FC1, and I want to use ReLU activation function here. Look at it, how easy it is. We are using tf.nn.relu. Okay, and then the second layer, right? I am taking input that is coming from FC1. Look at it, and again adding 500 hidden units here. FC2 activation is again ReLU. Now let's add. So what happens is that sometimes we try to build very complex model, but we don't have data, enough data. But one of the famous regularization for neural network is called dropout. Are you aware of dropout? Dropout, are you aware of? No? So what happens is that, so I build neural network, right? I showed you neurons, right? So in dropout I say that I will kill some of the neurons at random, right? In every training step I decide to kill some of the neurons randomly. So some of the neurons will just not be present, they will not be updated. That's called dropout. Got it? So that's dropout. So I can simply say tn.nn.dropout. I apply dropout after the second iteration. Okay, with keep probability of 0.9 with a dropout probability of 0.1. And finally, I use the output of dropped. I use number of classes, and output I get y. Right? So this is, that's it. We defined our deep neural network model. Okay, so I think I did not run the earlier one. Run this. Okay. Now you evaluate, right? Again the similar thing, right? I try to find this out, and this is where we are training. Okay, so the neural network is training now. You see, we got accuracy of 97% on the test data.